Today in Physical Science 20 is limiting reactant problems. You may also read in your textbook or online, it may be called limiting reagent problems, the same thing. A reagent and a reactant are the same thing. They are substances that will react in a chemical reaction. They're the substances on the left side, okay? These are the reactants here on the left side of the arrow, the reactants. So what is a limiting reactant problem involving? Well, in real situations, we don't always have an excess of one reactant, okay? Not always. And the stoichiometry problems that we've done so far, if you've recalled, I give you, some kind of equation and I say you have so many grams of A, and then you have an excess of the other one. So you don't have to worry about this limiting the amount of reaction here for A. And that's what we've done so far, okay? But in real life situations, sometimes, most of the time, we have definite amounts of two or more reactants. So we have an actual limited amount of the reactants involved. So, for example, if you're doing a recipe, okay, and again, this is just kind of totally off the wall here, but if you're doing a recipe and you need, 1 cup of flour and you need, 6 eggs, okay, and, you have 3 cups of flour and you have 15 eggs, okay, so how many, let's say this produces, I don't know, a dozen cookies or something, let's say this is how you get a dozen cookies, how many dozen cookies, full dozen cookies, we'll be able to make? Well, we've got 3 cups of flour, so you might say, hey, we're going to make 3 dozen because I've got 3 times as many flours. Well, do we have 3 times as many eggs? No, we don't. So you see how 1 is a limiting reactant? We do not have enough eggs to make 3 full dozens here. We can only make now 2. Can we make 2? Yes, I have at least 2 cups of flour. And do I have at least 12 eggs? Yes, I do. So I can make 2 full dozens. And what I had to do was consider how much of each reactant I have, or more appropriately, the multiples of each reactant that I have. Okay? And this is a sort of a side example of a limiting reactant. But if you can get that in your head that, hey, something is going to run out first, right? So whichever one runs out first, that's the limiting reactant. And that's also going to dictate how much product I'll get. Make sense? Okay? So in a limiting reactant, we have to calculate the reactant that is used up first. And that is the essence really of what we're looking at here. So which one, while these two things are reacting, which one is going to get used up first? So I did the baking example, which I know nothing about baking, as you can tell. 1 cup of flour, 6 eggs for a dozen cookies. Does anyone know if that's at all around there? Nothing close. You wouldn't need 6 eggs for a dozen cookies, right? You'd need like 25, right? I'm kidding. 2. Okay, 2. Good job. All right. So 1 to 2 would have worked well too, because look at, we have a 1 to 2 ratio in this example. So let's take a look at the example. All right. So now got a lot of marking on here. I'll erase some of it. All right. So in this example, I've got 1A. So that is 1 mole of A has to combine with 2 moles of B to produce 1 mole of C. All right? So now here's the situation. The example is I have 1.1 moles of A. That's what I'm given. Okay? So here is given. And I have 1.4 moles of B. That's what I'm given. The recipe or the ratio says that A and B have to react in a 1 to 2 ratio. So here we need to find out which one's going to run out first, or which one is going to be the limiting reactant. Now, I've kind of given away a little bit of the answer here. This is from the previous lesson. But if I have 1.1 moles of A, how many moles of B will I need to react with that? The answer is 2 times, right? So 2.2. Do you see how this is a 1? I need times 2 to get the number of moles there. So this times 2. You see that? So this is the minimum amount of B that I need to react fully with A. And the question you're going to ask yourself is, well, how much B here am I given? I'm given 1.4 moles. Is that more than 2.2 or less than 2.2? Okay, yes, it's times by 2, but we're not multiplying this one by 2. Okay, so let's go back just one more step. Let's go back. If I'm given 1.1 grams of A, because this is a 1 to 2 ratio, that means that I need 2.2, sorry, did I say grams? I meant moles. 1.1 moles of A, I need 2.2 moles of B to react with all of this. It's like this 1 to 6 ratio. You see that? If I have one of these, I need 6 of these. I have one of these, I need 2 of these. So if I have 1.1, I need 2.2 moles of B to react with it. And in this example, we see that I am only given 1.4 moles of B. So in this case, all right, reactant B is the limiting reactant because it gets consumed first. The reactant that gets completely consumed first is the limiting reactant. So in this case, and I'm going to run through the steps here, okay? So I'll kind of run through the steps on how we did that again. So in this example that we have, we take the first reactant, and this is just one method, but I like thinking about it this way because this is more closer to reality. I don't want to show you just all these fancy shortcuts and have you not understand anything. So this is what I do. Take the first reactant that we're given, and just check to see, okay, take the first reactant, check to see how much of the second reactant we would need to completely react with what's given. And that's what I did here. I have 1.1 of A. I need 2.2 moles of B according to this ratio 1 to 2. Does that make sense? 1 to 2 is the same as 1.1 to 2.2. So I need that much. So you check to see how much you would need. And in this case, of course, we calculate here that we need 2.2 moles of B. Now, the fact that we only have 1.4 moles of B means that we don't have enough for all of A to react. Okay? So B is going to be the limiting reactant. See, B is going to get used up. The 1.4 moles is going to get used up before all of the 2.2 moles. The 1.4 is going to get used up before the 1.1 does. So B is the limiting reactant because we don't have enough of it to react with all of A. So write this down, this is really important. B is the limiting reactant because we don't have enough of it to react with all of A. The one that has stuff left over, okay, so if we have left over, now this is, actually I won't read this sentence because I don't want to confuse you about the reactant excess yet. Okay, but I'm going to do this example here right now, so just skip that sentence for now. Let's just take a look at this example. Okay, so this one says, here's the example for limiting reactant, stoichiometry. It says, find the limiting reactant when 2.8 moles of nitrogen, you want to write this example down, please. So you're given 2.8 moles of nitrogen, burns in air, and that is, you're given this much air, so oxygen, 9.22 moles. Produce nitrogen dioxide. So let's just write that. Nitrogen is N2. It burns in air, that's O2. And it produces nitrogen dioxide. Okay? Nitrogen dioxide. So we need to balance this, right? I need 2 oxygens here, or sorry, 2 nitrogens, because I have 2 over here. And I have 4 oxygens now, so I need another 2 there. So this is our balanced equation. Okay, now the steps, I'm just going to skip down to the steps here now. Step number 1 says determine the balanced equation, so that's what we did. So number 1, determine balanced equation, step number 1. Number 2, make sure all amounts that you're given are in moles. So we might need to convert, right, grams to moles. We might need to convert. So we've got 2.8 moles of N2, that's good, it's in moles, and 9.22 moles of oxygen. All right, so now the third step, this is sort of the big deal here, right? Find the limiting reactant by choosing one reactant to test the ratio. So the first one that I'm given is nitrogen. So to test the ratio, we would go like this: 2.8 moles of nitrogen. All right. How many moles of oxygen would I need? According to the balanced equation, which is right here, it's 1 to 2. So if I had 2.8 moles of nitrogen, the recipe says that I would need at least 2 times that, or 5.6 moles of oxygen. You see that? To complete that 1 to 2 ratio. So that's what you do. You test. And then you ask yourself, do I have at least 5.6 moles of oxygen? Do I have more than that or less than that? And you'd answer yourself and you'd say, hey, I have 9.22 moles. I have way more than 5.6. So that means I have extra oxygen available. If you have extra oxygen available, then the nitrogen is going to get used up first. All right? Sometimes a little diagram helps, okay? So watch this. I have this many moles of N2, and I'm combining with oxygen, and I need double the amount. So this is like a little bar graph here. I need, let's say, 1 to 2. You see that? So if, let's say, that the 2.8 moles represents the 1 for nitrogen, that's all of the nitrogen, I need 5.6 moles of oxygen. You see that? 1 to 2, 2.8 to 5.6. And how many do I actually have? Well, I actually have 2.8, and I actually have like 9.2. See that? I have way more oxygen than I need. So that means that the nitrogen is going to get used up first, because only this much oxygen is going to get used. Does that help? Like, you really have to use your brain. This is not like a formula that you just write down on a cue card and just not look at it until you have to, write an exam. This is like, are you understanding? Am I understanding? So it does take some focus. I know you guys are working real hard. If you have any questions right now, does anybody have any questions about anything? Anything a little fuzzy so far? So again, I'm not kind of giving you a magic bullet just to plug into a formula and figure this out. But that's how you would do that question. That's all. Which one is the limiting reactant? We determined that nitrogen is going to get used up first. Okay. So that's what I'm suggesting. This example here, okay, I'm going to just kind of move through this example here. That's just kind of an extension there. Okay, and method 2, not going to talk about method 2 right now. That might be for another lesson. Instead, let's do another example, and I'll hand out your assignment so we can start working on that first question together. Yeah, you can copy down this sentence here, everyone, because put a little star beside it maybe, just kind of as a note, because this talks about the reactant that would be in excess. So just take a moment to jot that down in your notes. You'll be able to look back to this and it'll make a lot more sense after we do some more examples. Okay, so here's the formula, the equation that we're going to use for the first question. First thing we got to do is balance, right? Always we deal with a balanced equation. So the carbons, I look at the carbons here, and there's 3 here, so I'm going to put a 3 there. So the carbons are balanced. Let's leave the oxygens for last, because the oxygen's all by itself here. So what about the hydrogens? We have 8 hydrogens on this side, and we have 2 here. So let's multiply that by 4. And then how many oxygens do we have in total? 6 plus 4 is 10. So I can put a 5 there then. And a 1. We done? Does that look good? Okay, 1, 5, 3, 4. So that's the molar ratio of everything involved in this equation, right? We know that we now have a 1 to 5 ratio of reactants. Okay? 1 to 5. That means I need 5 times as many moles of oxygen to react with this right here. Okay? Does anyone know what this molecule is here? You might know. What's that? Yeah, C3H8. You know what the name is? It's a hydrocarbon. It's propane. Yeah, methane, ethane, propane. So meth is one, ethane is 2 carbons, and propane is 3 carbons here. So that's propane. So we're burning propane. We're going to have barbecue. Okay, throw some burgers on, some dogs on. This is what you're burning. Okay, greasy ones, yes. All right. So the question says, if you have 14.8 grams, it's not a lot, but not going to quite cook a whole hot dog. But anyways. Of propane, and you have 3.44 grams of oxygen. The question is, what is the limiting reactant? Okay, so what is the limiting reactant? All right. So in this question, what we need to find out, first of all, is we need to convert to what? Moles. Very good. Yes, we always have to convert to moles first. So I've got 14.8 grams, and I need to divide by the grams per mole of propane. So let's take a moment to do that. Okay, so you divide by the grams per mole, C3, so that's 3 carbons times 8 oxygens, and I did that all in one step on my calculator. I got 0.335627 moles. Is that, how many, put up your hand if you got the same number. Okay. You don't have to write down all the decimals. That's 3.3. Sorry. 5.6. You don't have to write down all the decimals on your paper, but write down 4 or 5 decimal places at least, and keep this number on your calculator so you can use the whole decimal in your calculations if possible. Okay, so I'll put 2.7 here. Okay, now this is moles of C3H8, right? Now let's convert on this side moles of oxygen. So we've got 3.44 divided by 2 times 15.9994, and what do we get there? Okay, so this one looks like oxygen. We've got 0.1075 moles of oxygen. Okay, so now this is where you have to understand kind of what's going on, right? And you have to say to yourself, which one is going to run out first? And you look at your mole ratio, and you need 5 times as many moles of oxygen. If I have 0.335 moles here, I would need, okay, times 5, right? Moles of oxygen. So, I mean, you don't, I mean, if you might notice already, I don't even have to do this on the calculator to check, but let's just say times 5, okay? So I need 1.6 moles. That's 1.6 moles of O2. Do I have 1.6 moles? No, I have 0.1 moles. So the fact that this number is even less than this number, and you know you need 5 times more, okay? So which one do you not have enough of? Of oxygen. So does it make sense that oxygen is the limiting reactant? Okay? So again, if we use a little bar graph here, this is 0.33, and I need 1.6 of oxygen. Well, I only have 0.1. That's all I have. So guess what? You're not even going to be able to use, you know, what's actually going to get used is just this much that I've highlighted in black. That's it. Right? And so certainly, you know, this is going to run out first because I have just a very little amount. So, okay. So yeah, so the barbecue is only going to be on for a couple seconds. All right. So which one's the limiting reactant? Well, O2 is the limiting reactant because I do not have enough of what I need to fully react with the propane. Okay, and right now you can just say O2 is limiting reactant, and you know this is the work that you showed. Okay, so you could say, you know, not enough, right? Okay, makes sense? Now, the next phase here in noticing which is the limiting reactant, and this is the next big step, okay? It is determining, and the next part of this question is asking you how much carbon dioxide will then be produced, okay? So how much carbon dioxide will then be produced? So let's take a moment to just write that question. So now as we actually, now this is actually now the stoichiometry, right? This is the stoichiometry, but what we know is that we know that 1 is going to be the limiting reactant, so we can't use the number of moles of propane because we aren't going to be able to use that all, right? We're going to be able to use all of the O2 because that's the limiting reactant. It's going to get used up first. So when we're actually doing the stoichiometry now, you must use the limiting reactant amount. Okay, so use limiting reactant amount of moles in your stoichiometry calculations now. That is super, super important. Okay? So that means that the number of moles given, right, and we calculated that already, 0.1075, that's the number of moles that we use in our stoichiometry now, 1075 moles. Okay, so use the amount of the limiting reactant amount. And so we need to go, we're given moles, or we've already calculated moles, I guess, in the first question. So now I need to convert to how many moles of carbon dioxide I'm talking about, right? And you remember for stoichiometry, how do I calculate this number of moles? We use the molar ratios now. So what do I multiply this number by? 3 over 5. Yeah, 3 over 5. Remember, we take this number that we're going to, and you divide it by this number that we're coming from. That's how you get this ratio. Always. That always works. All right. So let's go back to the calculator here. And where was that number? Let's see. Entry. Nope. Let's try another one. There we go. So that's the full decimal there. I'm going to times 3 divided by 5, just like that. And I'm going to get 0.0645. 0.0645 moles. So in this question, how much CO2 will be produced? If it doesn't say, you can just say moles. But it might say, and in this question I'm going to say, I want the amount in grams. Okay? So that calculates our number of moles. And then, I don't have a lot of room here in my flow chart, but I need to go back up to grams, right, of CO2. And how do I convert moles to grams? Who remembers? Multiply, that's right. Multiply by what? Times grams per mole, right? In this case, it's going to be of CO2. So our grams per mole is going to be 12.011 plus 2 times 15.9994. So I'll let you take a minute to calculate that. And do you get 2.83? So 2.83, if we were dealing with significant figures, if we look back to our sig figs, we're given 3 sig figs in the original question, so let's go to 3. So that would be 2.84 grams. Grams of CO2. Make sure you circle your answer, please. And that's what the question would look like. So today's lesson is talking about limiting reactant and also how to find, but also how to use that information to do your stoichiometry. So just remember this. Always use the limiting reactant amount of moles in your stoichiometry calculations. You cannot use the amount of moles that were given here because they do not all react, right? So you can't go 1 to 3 using this number of moles because this is excess. There's going to be stuff that's not reacted. There's going to be leftover stuff. So you have to take the limiting reactant because this is all going to get used. We know that. So all of it gets used, and this is what gets produced. Okay? On your assignment, you have a third question here, and that third question says, how much excess reagent remains? So how much excess? Now, how we find that, out is this, okay? So you go back to your original question, and you look at the moles, right? You look at this molar ratio, and you say this is the limiting reactant, okay? So if I were to work backwards now, and if this was the top end of the 5, right? And then how much propane will actually partner with this, so at the 1 to 5 ratio. So this is when you can write down something like this, right? You say, okay, so 1 to 5 is the same as x to 0.10, what was it, 1075? Okay, moles. And so if this is a 1 to 5 ratio, I'm going to calculate how much propane that actually is going to go with this. And so x is going to be 0.1075 divided by 5. It's actually 7504031 divided by 5. So what's actually going to match up with this is going to be 0.0215. So x is 0.0215. And now that's going to be the moles of C3H8 that are actually going to get used, right? Because it's a 1 to 5 ratio. You see that? So in this question, how much excess reagent remains? Then you would simply go, what am I given for the propane? This number right here, 0.335627, 0.335627 moles, minus 0.0215 moles that are actually going to get used. So the question was, didn't we have 14.8, but that was grams, and we need to use moles because this is moles here, so we need to use the moles that we calculated. And then when you do that subtraction, that's going to be your leftover, right? So 0.335627 minus our answer there. It's going to give us 0.314126. And that's going to be your moles of C3H8 that remains. So just be clear what your answer is. Okay? So that is all of question number 1. Now you have 3 questions like that in your assignment. I'm going to give you the rest of the class, which is not very many minutes here left. But this is your limiting reactant lesson here today. You have a quiz. You're going to have a quiz on this stuff. Yeah, Wednesday.